So again, as I said, we're going to talk about energy. So this is the what the chapter look like in your. I guess this is too much, too fast. I just want to show you maybe the first page. Okay, so this is energy. Okay, and you see that there's a totally 8 sections, but we may not go through all of them because we're going to leave away some of the sections. So anyway, let's talk about this. Okay, chapter 5. Energy. Okay. So what is the big picture here? Okay. So far we've been talking about the two kind of, we've been talking about mechanics, right? Which, as we know already, is to study motion. Okay. And we've been talking about basically two questions. One is kinematics. The other one is dynamics. Basically, this is about the question of what is the question of why, right? So this is chapter 2 and 3 for 1D and 2D case, and this is chapter 4, okay, Newton's law. Okay, so in some sense, we're done with mechanics. So with Newton's law and then the kinematics we talked about in chapter 2 and 3. In principle, we could go ahead and solve all problems in Newtonian mechanics or classical mechanics. So it's something we're complete in terms of material. However, it turns out that there are some advanced topics that really worth to talk about. And so we're, in some sense, we're entering the second half of this course, advanced topics. So in chapter 5, we're going to talk about energy. And then chapter 6, we're going to talk about momentum. In chapter 7 and 8, we're going to talk about rotation. And then we'll talk about maybe a little bit angular moment, but I'm not sure. So these are kind of advanced topics. Okay, so these two, energy and momentum, we're just introducing some other concepts that turns out to be very convenient to have, and then actually a lot of cases provide us simpler or simpler way to solve our problems. So that's why I'm saying that it's not going to getting harder. In some sense, it's going to get a little bit simpler because that's why we want to introduce them in the first place. Well, this chapter 7 and 8 is we're focusing on a specific kind of motion. So far, we've been talking about motion in general. Everything we talk about here applies to all kinds of motions. Doesn't matter what it is. It could be a projectile motion, like linear motion, or it could be a rotation, or it could be an oscillation, whatever it is. But it turns out that when you talk about a specific kind of motion like rotation, you can introduce even more quantities that are convenient to describe rotation to give you a better understanding about rotation. So that's going to be a lot like the last part of the topic. So, and because they're advanced topics and because our time are kind of limited, so we're not going to go as thorough as we did before for these for these chapters. Okay, so in each chapter we're going to pick up some important topics and talk about them, and then we may leave out a lot more and more subject. Okay, depending on how we run, and especially in the summer because everything's really condensed. So even though in principle we have the same number of hours in lecture, but we might go a little bit lighter because otherwise too much. So I think we'll do a pretty thorough discussion of energy for chapter 5, but for chapter 6, momentum, we might just briefly mention it. We might ignore a lot of stuff in momentum in this chapter. Okay. Well, for chapter 7 and 8, I guess we'll we'll pick up some topics for rotation that's kind of fundamental for us to do. Okay. Now I know some of you take this class because you need to take the MCAT or whatever test you need for medical school or dental school or something. And I mean the reason we cover these is also some of the topics are probably, I mean, they're included in those tests. So that's why I won't do that. Okay. Okay. Without further ado, let's start from energy. Okay. So what is energy? Okay. Again, this is something we use every day without knowing its specific meaning. When we think about energy, right, we think about something that, we think about oil and gas, we think about nuclear, I mean, energy or nuclear weapon, we think about electricity, right? We think about this something that kind of like can do something for us, like certain material or certain matter, you know, it can do work for us or whatever, it can produce something, you know. And energy turns out to be the most important concept in physics, okay? And in some sense, even more important than force and Newton's law we studied in chapter 4. Okay, force is kind of a central for Newtonian mechanics. But if you go to other branches of physics, certain branches they don't talk about force, they don't have force, or at least it's not convenient to talk about force. But they always have energy. Okay, in some sense, each branch in physics has this, talks about certain kind of energy you can have. Okay. Or more than one kind of energy. So different branches in physics talk about different kind of energies you have. So that's how important this concept is in physics. Okay, so if I were George Lucas, I wouldn't call force as the ultimate reason for in the universe, like in the Star Wars. I would probably say energy, but I guess I don't know. Maybe he dropped off after Newton's law in physics 1, so he didn't get to know this. But I was kidding. So anyway, so well, you heard about this word a lot in everyday news as well, right? They talk about energy crisis, they talk about clean energy, they talk about fossil energy, not very clean, and then they talk about all kind of things about energy. So, and for human civilization, in some sense, we're in the way we advance, you know, science and technology is that the more we can control and we can use different forms of energies, right? So in the Industrial Revolution, we use the steam engines, right? It's essentially by burning something, getting a really hot, heating up water to steam, those steam can do work for us, right? Well, essentially that comes, the burning coming from the coals and the wood and finally oil and gas, oil, mostly oil. And these are basically one kind of energy, right? And then later on we have electricity. We would be able to use, we would be able to produce electricity using other kind of like water power, wind power, and then even closer, we got atomic bombs, nuclear bombs, and then we got nuclear plants to kind of create electricity out of it, right? And then all this kind of stuff. So energy is everywhere, okay? And okay, so I guess probably we don't need to talk about that much about this general thing. So the first topic we need to talk about in this chapter is actually called work. Okay, with that is give us a easy entry to understand the energies and what a specific kind of energies in this class. So what is work? Again, this is another word we use every day, right? You need to work harder, you need to do your work, et cetera, et cetera. But in physics, it has a different meaning. So specifically, what we talk about in this class called so-called mechanical work. So what is that? Okay, so let's try to define it. But with a some demonstration or something. Okay, so let me grab something. Okay, maybe let's use this toy car here. So again, this thing at rest, right? Now, if I push it, it's gonna move, right? if we consider this motion, okay, there's this pushing force on the car. Okay, so what can we say here? So we like to say that we want to, one thing we could consider is this. Okay, so let's draw it here. So this is something that, I mean, I guess we would ignore the wheels. It could be for other objects as well. So let's say you have a force, okay, you're pushing the car or pulling. Now under this pushing, right, or pulling, the car make a displacement, okay? Let's call this a D here, okay? So one thing we could talk about is what is the contribution of the force to this motion, okay? So what's the effect of the force? What is the impact of the force to the motion, okay? Impact of the force to the motion, okay? Well, in this specific case, it's pretty clear that this pushing force or pulling force is critical to the motion, right? Without that, without this force, this thing wouldn't go, right? You're pushing it. So it is obviously has a huge impact. It has a huge contribution to the motion, okay? So in order to calculate it, we'll simply put it like put the force here and then the distance here. We multiply these two together, okay? And we define that as our work. So the work is, or mechanical work, is defined as the force times the distance. Okay, it's pretty simple to understand, right? So certainly the bigger the force you have, the bigger work it does. I mean, for the same distance or for the same force, if the thing goes longer, the bigger work as well. So that's a way to quantify the impact of force. Now, another question we can, I mean, however, it's not the full story here. Okay, like in a different case, I mean, consider, I mean, in the same motion, right? I'm going to draw it again here, okay? Well, as the object moves, there's some other forces acting on this object as well. For example, there's always gravity, okay? Same displacement, same distance travel, okay? Now, if you look at gravity, right, there's actually also normal force here as well, right, as we know. But if you look at these two forces, okay, do they have a direct impact to the motion? Yes or no? What do you guys think? Just send me a message. Tell me either yes or no. Okay, we have different answers. Some people say yes, some people say no. Okay, but think about it, right? When this thing is here already, right? Without my pushing force, this thing staying here, there's no motion, but they still have the gravity and normal force, right? They're already there, but they could not produce the motion because they're going on along the vertical direction and they cancel out or whatever. So they cannot produce the motion. But so in this sense, I would say they do not have a direct contribution to the motion. Mostly because they're going along the direction that's perpendicular to the direction of motion. So as we know from the previous chapter, the X and Y direction are kind of independent from each other. Whatever force you have along the Y direction would create whatever acceleration along the same direction. Whatever force you have along the X direction would create acceleration along the X direction. So they do not kind of overlapping, or there's no interactions or something, interference. So we would like to say, okay, this, we call this work by this F force here, okay? We would like to say that the work done by gravity equals to 0, and work done by normal force equals 0 as well, because they don't have direct contribution to the motion, okay, or they don't have direct impact to the motion, okay. So these are a couple of different cases we have, okay. Now, how do we kind of put them together and give a universal definition for work that satisfy all these different cases? Turns out we can, and again, for that purpose, we need our old friend of trigonometry, okay. Now, hopefully by now, they're already your friends, now they're enemies. Okay, so so we'll define work in general like this. Okay. This is for general, a force given by, I mean, a work given by any force, okay? We use this as our definition for work, okay? Now, what does this mean? Okay, how do we go back to the previous cases, okay? So if I go back to the previous case, in the first case here, right? So, okay, firstly, let me explain this angle theta. This angle refers to the angle between the direction of the force and the direction of motion, okay? Say this is your direction of motion, this is direction forward, this is the angle between them, okay? So let's go back to our first case. In this case, we have a horizontal force pulling it. So the angle between the direction force and direction motion here is simply 0. And cosine 0 is 1, okay? So for the first case, because cosine 0 is 1, so you have W equal to FD. So that's gonna be our formula for this, for the work, okay? What about the second case? Okay, in this case, the motion is going along the same direction in a horizontal direction, but the gravity and normal for they're going on the vertical direction. So the angle between them are 90 degrees. Okay, so okay, cosine. Let me write here. Cosine 0 is 1. Cosine 90 is 0. Okay, you can easily check it by using your calculator. Okay, so because of this, when we calculate this work and this work, we plug in the angle here. It becomes 0. So the work is 0 for both. Okay. So actually this gives us the result like this formula takes care of all these cases. Okay. When you have a force doing contribution and when they have other force, have no contribution. So this formula is general. Okay. And that's going to be our definition. Okay. But again, my point here is when you try to understand this concept, try always to think about the contribution of the force to the motion, right? And don't just think about like very abstractly this formula here, okay? Now you can understand this formula from a different point of view, okay? If you rewrite it like this, okay? So what is this part here, okay? Well, F cosine theta, if you look at this triangle here, right? So this is F, this is theta. F cosine theta goes to give you this component here, okay? So see, only one component of your force is doing the work, okay? The other component, which is F sine theta, going along the perpendicular direction of the motion, that won't contribute at all. So only F cosine theta contributes. So that's also kind of how we would understand the meaning of this of the work. Again, to have a non-zero work, you have to have a component of the force going along the direction of motion. Okay, otherwise this force is totally irrelevant. Okay. So let's talk about some other cases you can have. Okay, now think about it, right? The angle between the force and the direction, it could be any angle between 0 to 180 degree. Okay. Well, so far the case that we have is, I mean, this case is 0 degree. This is a 90 degree, right? So these are all you have when it's 90 degrees 0. When it's a 0 degree is positive. But what about some other angles? Well, it's pretty clear when angle theta is larger than 0 but smaller than 90 degree. Okay, so we talk about, okay, maybe let me put a full list here. Okay. So when theta equals 0, cosine theta equals to 1. So you have this, the first case, you know, you have the maximum contribution from the, so it's a maximum and positive contribution. Okay, now another case would be when theta is larger than 0 but smaller than 90 degree. Okay, in this case, cosine theta is a number between 0 and 1. Okay, so you still have positive contribution, although it's not going to be maximum positive contribution because one component of your force not doing the work. Okay, Okay, then we have case when theta equals to 90. And in that case, we see that cosine theta is just 0. And then we have 0 contribution, okay, to the force. The force has 0 contribution. So the work is 0, okay. So maybe let me put this, W equals 0. So this is W equal to, W is larger than 0, and this is also W larger than 0, okay. So this case, the third case corresponding to when you have a gravity and normal force going opposite directions, okay, I mean, going perpendicular directions, okay. Now, but there's some other interesting case when theta is larger than 90 degree, but smaller than 180 degree, okay. Turns out cosine theta in this range is gonna be larger than -1, but smaller than 0. So it's gonna be a negative number. What does that mean, okay? If you plug in the cosine theta here, you get a negative number here, okay? While your force and distance, they are always positive, okay? Keep in mind, when we plug in numbers for F and D, you should plug in for the magnitude of the force and magnitude of the displacement. So these were always positive. The sign come in for this cosine, so cosine theta. So in this case, the force is going to be having a negative contribution. Because W is smaller than 0, okay? Well, example of that would be like, say, if you have a object going this direction, you know, going forward like this, with this and D, but you have a force you kind of try to slow down the object, like by pulling it backward. This angle here, certainly, this angle theta is going to be this case. It's larger than 90 degree, but smaller than 180 degree, okay? So in this case, this force has a negative contribution. You calculate the work done by the force, you get a negative number, okay? Finally, we have a case when the force is when theta equals 180, okay. In that case, cosine theta equals to -1, okay. So in this case, the force has a maximum negative contribution. So W is still smaller than 0. Okay? In that case, actually corresponding to a case that when you have a force, see the object moving forward, but the force is going backward like this. Okay. Well, certainly that could be kinetic friction, right? Kinetic friction is a perfect example of that. Okay. So so hopefully by these kind of cases, you can kind of see that how this definition applies to different cases, and then to give you different numbers. Okay, and before we do an example, let's also talk about the unit. Okay, so we have a W equal FD, right? So the unit for force is a Newton, right? So force you have Newton, and then distance you have meter. So the unit for work is going to be Newton times meter, okay? And in this case, we give a special name for it. We call it joule. Again, this name comes from a physicist, Joule, and he actually studied a lot about work and energy. He did a lot of contribution in that case. So we use his name to name this thing. So, okay, last question. We have 5 minutes. So, do you guys think this new quantity W work? Okay, is work a scalar or a vector? Okay, send me a message. Okay. Okay, I got one answer. Anybody else? Okay. Now I got 3 different answers. 2 says vector, 1 says scalar. Okay. Actually, it turns out work is a scalar, not a vector. Okay. Now, why is that? Because it's not easy to define the direction of work. Okay. Well, based on what we're talking about here, see, when we talk about the F times D, these are all magnitudes. Okay. Well, the cosine theta give us a sign. Okay, it could be positive or negative, but with a sign doesn't necessarily mean it has a direction. So, for example, when we talk about temperature, right, you could have a positive 60 Fahrenheit or a negative 10 Fahrenheit or whatever, but temperature is still a scalar because it has no direction. Same thing, work is also a scalar. Okay. and keep that in mind. Okay, the reason for that, I mean, it's actually one reason we want to work with work instead of forces, because forces are all vectors. To actually do the force, we have to use Newton's law. You know, we have to solve problems. I mean, with vector, consider components, directions. It's going to be pretty complicated. So one advantage of work and energy as well is because they're all scalars. They're easy to work with. They're just like a number. Okay. Now I realize there's another example here. A question I want to ask you guys before we finish today's lecture. So let me give you one last question here. Okay. So let's take this very heavy pack of paper. So let me ask you this. Okay. If I hold it in my hand like this, okay, for 5 minutes, based on what we discussed today, how much work am I doing? A positive work or a negative work to this piece to this pack of paper, to this pile of paper? If I just hold it steady in my hand, send me a message. Do I do positive work, negative work, or whatever, zero work to this pile of paper? Okay, I got 2 answers. Okay, I got 4 answers. It turns out only one's right. So it turns out there's no work done on this pile of paper, because if you go back to this definition here, right? So see, force times distance times cosine theta, right? Well, as I'm holding it, there's no distance traveled by this pile of paper. So D is 0. So in this case, the work is 0, okay? You may say, this is totally unfair, because when I hold it, when you hold it, whoever hold it, right? After a while, you feel really hard, you know, you feel your arms are sore, like your muscles couldn't sustain anymore, you know, you feel like you're doing work, okay? How come it doesn't come here, okay? The answer is actually, going back to this, what we're talking about in this class is totally mechanical work, okay? So it's mechanical work is the work that related to the mechanical energies. So in this sense, this one does not count, okay? Well, certainly by holding something in your hand a long time, you could actually, you actually use your energy of your muscles, okay, like ATP or whatever kind of energy it give you, and then it certainly help you to maybe lose your weight or something. But these are beyond the scope of mechanics that we're talking about. This is more like chemical energy. Doing something with chemical reactions and everything. So this is not included in this discussion here. So in this discussion, we focus on mechanical work and mechanical energy. And remember, mechanical energy, it's stuff like mostly related to motion. So it does not count as mechanical work. Okay. Okay, I think this is it for today.